Welcome back to our next lecture on DSP. In the last two classes, we have discussed about the frequency response and linear constant coefficient difference equations. Today, we will see the frequency domain and linear constant coefficient difference equations related problems. Today, we will see the problems on frequency response and also LCCDEs, means already you know that the linear constant coefficient difference equations. I'm just briefing about frequency response and LCCDEs equations. The frequency response is nothing but a combination of magnitude and phase response. And you know that the magnitude response is denoted as root of real square plus imaginary square coefficients. And the phase is nothing but tan inverse of imaginary by real terms. In the last class only, you have discussed about those. And coming to the linear constant coefficient difference equation, it is the equation which represents the any digital transfer function. Means the linear constant coefficient difference equation. Whereas in the analog communication or analog thing, we will use the differential equation. Whereas in the digital, we will use difference equations. The difference equation is nothing but a linear constant coefficient difference equations. So for this, we have assumed that for homogeneous solution, you have to keep input x of n equals to 0, and you have to assume y of n equals to lambda power n, and you have to find the roots for that. And according to the roots, if the roots are equal, are distinct and equal and same, like that we have different complex conjugate, like that you have conditions. And again, you have to find the natural response from that response, homogeneous response. So for this, how we have to apply for the difference equations, for different difference equations, how to apply this LCCDEs and how to find the frequency response of the system. So coming to the first problem, if you see here, the problem is describing a discrete time system has a impulse response h of n equals to 1 by 2 del of n plus del of n minus 1 plus 1 by 2 del of n minus 2. Here, a discrete time system has an impulse response h of n is what? It's a combination of 1 by 2 del of n plus del of n minus 1 plus 1 by 2 del of n minus 2. Here is asking find the frequency response h of e power j omega of the system and determine the magnitude and phase response, and also plot the magnitude and phase of the response, that is h of n. Here you have to find the h of n, magnitude response, phase response, and how to plot these two. Yes or no? So from here, it is clear that in the last class we have discussed about how to find the frequency response. The frequency response of the system is obtained by keeping z equals to e power j omega. We have to substitute e power j omega. But if you see here, the h of n is given in the form of n, means in the time domain. So you have to apply the z transform on both sides to make it has in the form of z's. So if you see here, the z transform of h of n is the h of z and equals to 1 by 2, and the z transform of del of n is equals to 1, and z transform of del of n minus 1 is equals to z power minus 1, and z power of del of n minus 2 equals to z power minus 2. Means whatever the coefficient, if you see here, z of del of n minus capital N is equals to z power minus n. So like that, I am applying the z transform for the above h of n response, that is z transform of h of n equals to z transform of 1 by 2 del of n plus del of n minus 1 plus 1 by 2 del of n minus 2. So for this equation, I have applied the z transform on both sides. So what will happen? So z transform of h of n is nothing but h of z, and 1 by 2, by using the linearity property, you can divide these two, this all z transform of 1 by 2 del of n plus z transform of del of n minus 1 plus 1 by 2 z transform of del of n minus 2. So by applying the z transform, z of 1 by 2 del of n is 1, so 1 by 2 is the remaining, and next z transform of del of n minus 1 is z power minus 1, plus 1 by 2 is same, and z power of del of n minus 2 is z power minus 2. So like that, we have applied the z transform on both sides and we have find the h of z. This is the transfer function of a given difference equation. For the given difference equation, the transfer function after applying the z transform will obtain that 1 by 2 plus z power minus 1 plus 1 by 2 z power minus 2. So for this transfer function, we have to find the frequency and magnitude response. So for that, already I have told that for obtaining the frequency response, you have to keep z equals to e power j omega. So in the place of here no z, so h in the place of z I am substituting e power j omega. So h of e power j omega plus 1 by 2 z power minus 1 means e power j omega. Z is e power j omega. Z power minus 1 is nothing but e power j omega into minus 1, that is e power minus j omega. Similarly, 1 by 2 z power minus 2 is nothing but e power minus 2 j omega. If you see here, from here, I can take a common thing e power minus j omega. I'm taking e power minus j to omega. So what will happen here? No term related to e power minus j omega. So what I have to do? 1 by 2 by e power minus j omega, because no e power minus j omega, plus here only one e power minus j omega, that is common. So remaining is 1 plus 1 by this e power minus 2j omega can be written as e power minus tj omega equals to e power minus j omega into e power minus j omega. Yes or no? So this can be one e power minus j omega came outside and another e power minus j omega is remaining. So e power minus j omega 1 by 2, here 1 by 2 also available here. So 1 by 2 e power minus j omega is coming up, then e power plus j omega plus 1 plus e power minus j omega by 2. Yes or no? So from here, what I have doing, e power minus j omega into whatever the terms related to e power j omega, I am taking those into the one consideration, that is 1 plus 1 by 2 I am commoning. So e power j omega plus e power minus j omega is the remaining term. So as you know that e power cos theta equals to e power j theta plus e power minus j theta by 2, and sin theta equals to e power j theta minus e power minus j theta by 2j. So by applying this formula, we can write here e power minus j omega into 1 plus 1 by 2 means 1 by 2 e power j theta. In the place of theta, here we have available cos. So cos omega. So we have got e power minus j omega into 1 plus cos omega. Like that, we have obtained the h of e power j omega. This is h of e power j omega. So for this, we have to find the frequency response, that is nothing but magnitude response and a phase response. As you know that magnitude response is nothing but root of the real square plus imaginary square coefficients, and the phase response is nothing but the tan inverse of imaginary term by real term. If you coming to check here, I am applying a modulus to this term, means this term I am applying the modulus to find the frequency response. In that we have finding the magnitude response. So e power minus j omega modulus of 1 plus cos omega. So this is the in the magnitude we have to multiply the magnitude also. If the terms are in product term, then you have to while coming to the angle you have to plus. So if you see here, modulus of e power minus j omega 1 plus cos omega modulus. So e power minus j omega is nothing but by using, already you know that by Euclidean rule, cos omega plus j sine, here minus na, so minus j sine omega. So what is the magnitude of this term? Root of real square cos square omega plus sine square omega. It is nothing but 1. So that's why the modulus of e power minus j omega equals to 1, and the 1 plus cos omega is the real term, root of 1 plus cos omega whole square plus 0 square, because imaginary term is not available in here. So 1 imaginary is 0. So 1 into root of 1 plus cos omega square root cancel, then you have obtained the magnitude response is nothing but 1 plus cos omega. So now we will find the frequency response, phase response for the frequency response. So if you coming to that, angle of h of e power j omega equals to tan inverse of minus sine omega by cos omega. Nothing but tan inverse of, what is the imaginary term here? Sine omega. and the tan inverse of minus sine omega by cos omega. So that is nothing but sine by cos is nothing but tan omega. Tan inverse of tan is nothing but omega. So here minus indication. So minus omega is the what response? Phase response. So if you see here, magnitude is 1 plus cos omega of time and phase is omega. Okay. So for already in the problem he has asked that draw the and plot the magnitude and phase responses also. So we have to draw the phase response and magnitude response for different values of omega. For different values of omega. So I am considering omega values in the range of 0 to pi. 0 to pi. If you check here, by using your calculator, scientific calculator, check. See here. For omega equals to 0, what is h of e power j omega? Magnitude of h of e power j omega. So what is the magnitude? 1 plus cos omega. Here I am substituting in the place of omega. Magnitude response is equals to 1 plus cos of 0. Omega is 0 degrees. So cos 0 is 1. 1 plus 1 is equals to 2. So the magnitude response is 2. Similarly, if you substitute for phase response, that is nothing but minus omega. So what if the value is there? That will be the minus value. So here minus 0 or plus 0 same similar. So it is here 0. Coming to the pi by 6. If you substitute pi by 6 in the magnitude response 1 plus cos pi by 6 by and phase response is minus pi by 6 because just the replica of the omega. So magnitude is equals to 1 plus cos pi by 6. So by adding these two, we will get 1.86. For different values of pi by 4, pi by 3, pi by 2, 2 pi by 3, 3 pi by 4, pi. I am considering these are the omega values for plotting this frequency response. For different values, we obtain this frequency response, that is magnitude is different values and angle is different. If you observe here, the magnitude response of the system is decaying till 0. For 0 it is highest and for pi it is very low. Means the magnitude response is decreasing condition. So I am considering for magnitude response and x-axis I am considering the omega values. On the y-axis I am considering the magnitude of h of e power j omega. So what is the highest value here? 2. So what is the lowest value? 0. So I am considering 0, 0 0.51, 1.52, 2.5 and the same values of omega is these. So for different values, for 0 it is 2. So I am marking here. So pi by 6 1.86 like here. Like that I am marking all the values with respect to the omega values and I am plotting a magnitude response. Similarly, we have to plot the phase response. Here same pi by 6 and minus pi by 6, pi by 4 minus pi by 4. That's why I am taking downward axis. If you want, you can take upwards also, no problem. So this is the phase response for the given problem. So for this problem, this is the magnitude response and this is the phase response. Where the magnitude response is the 1 plus cos omega and the phase response is minus omega. Yes. Very good. Next, we are going to the next problem. Here also determine and sketch the magnitude and phase response of a y of a difference equation given by y of n equals to 1 by 2 x of n plus x of n minus 2. So here also first what we have done here, we have applied the Z transform. Similarly, here to apply the Z transform for this. Z of y of n equals to Z of 1 by 2 is constant. I am keeping outside x of n plus x of n minus 2. So Z of y of n is nothing but y of z and that is equals to 1 by 2. By applying linearity property, we can read it as like this. Yes. So now we have to apply the Z transform for this side. So y of z equals to 1 by 2 for x of n, x of z, and for z of x power x of n minus 2 means z power minus 2 into x of z. So from here I am commoning x of z. So y of z is nothing but x of z 1 by 2 plus z power minus 2. Just I am taking x of z outside from this summation. So y of z by this one I am taking this side, it will become by x of z equals to 1 by 2 plus z power minus 2. This is nothing but the transfer function h of z, that is equals to 1 by 2 plus z power minus 2. So this is the transfer function. Here also we have obtained the transfer function h of z. After obtaining h of z, we have to substitute z equals to what? E power j omega. So in the place of, if you substitute h of z is equals to 1 by 2 plus z power minus 2. So this is the 1 by 2 plus z power minus 2. In the place of that, I am substituting h e power j omega equals to 1 by 2 plus e power z power minus 2 means e power minus 2j omega. So after substituting for e power minus j omega is nothing but cos 2 omega minus j sin 2 omega, that is multiplied by 1 by 2. I am multiplying this 1 by 2 inside, and from here I am considering the real terms and imaginary term. This is the real term, this is the imaginary term. After that, it is easy to find the magnitude response and phase response of the given difference equation. So this is the real term, real part, and this is the imaginary part. So what is that? Magnitude response is nothing but root of real square plus imaginary square. So what is the real part here? 1 by 2 is common, so I am taking 1 by 2 is outside. 1 plus cos 2 omega whole square plus sin 2 omega whole square. So if you see here, it is elaborated here. 1 by 2 equals root of 1 plus cos 2 omega whole square plus sin square 2 omega. That is nothing but a plus b whole square, a square plus b square plus 2ab plus sin square 2 omega. Cos square 2 omega plus sin square 2 omega equals to 1. So 1 plus 1, 2, 2 plus 2 cos 2 omega. 2 common this, if you common this 2, 1 by 2, root of 2 into 1 plus cos 2 omega, that is 1 by 2. 2 into 1 plus cos 2 omega is equals to 2 cos square omega. So 2 into 2 cos square omega, 2 root 1 to root 2 and cancel, 2 by 2 is 1, and the remaining square root cancel cos omega. So magnitude is cos omega. So similarly, for phase response, substitute imaginary by real. So nothing but, what is the imaginary here? Sin 1 by 2 sin 2 omega minus, and 1 by 2 1 plus cos 2 omega is the real term. So remaining term is minus tan inverse sin 2 omega. Sin 2a is nothing but 2 sin a sin. So by substituting that, here one cos omega is cancelled, then tan inverse of sin by cos means another cos will be there. So tan inverse, similarly like at the previous problem only, the phase response is here also minus omega. Similar to that, we have to substitute for different values of omega. We have to find the magnitude response of the free system and angle of the system. For this, we have to plot this. Okay. Next, coming to the problems and linear constant coefficient difference equation. As I said earlier, for obtaining the homogeneous equation, here if you see, find the natural response of the system described by the difference equation y of n plus 2, y of n minus 1 plus y of n minus 2 equals to x of n plus x of n minus 1. This is the difference equation given in the problem with the initial condition y of minus 1, y of minus 2 is equals to 1. For this, you have to find what? Natural response. We know that the natural response is the combination of homogeneous response plus impulse response. So here we have to consider this equation, that is this equation. For the homogeneous equation is obtained by keeping the input terms equals to 0, that is x of n equals to 0, that is x of n and x of n minus 1 is 0. So then what will be the answer? So y of n plus 2 of y of n minus y of n minus 2, this term becomes 0. So assume for obtaining the homogeneous equation, we will assume y of n equals to lambda power n. So if you substitute here, y of n is nothing but lambda power n and plus 2 into lambda power n minus 1, because y of n is lambda power n, so y of n minus 1 is lambda power n minus 1, and y of n minus 2 equals to lambda power n minus 2, like that will come. So y of n minus 2 is equals to lambda n power minus 2 equals to 0. This is the sum. So here from here I am commoning the lambda power n minus 2, then what is the remaining sum? Lambda power n minus 2 by 2 means lambda square plus 2 lambda plus lambda equals to 0. I am considering this to the left side, so it becomes 0. So lambda square plus 2 lambda plus 1 equals to 0. If you find the roots for this quadratic equations, and we will get lambda equals to minus 1 minus 1. That is the term you have to know here. The roots are real and equal. The roots are real and equal. And according to our condition in the linear constant coefficient difference equation derivation, if it is the roots are equal and real, the homogeneous solution should be like this. Means minus 1 whole power n c1 plus C2n. If it is another root is there, C1 plus C2n plus C3n square. Like that we will write them for the another root. So if you coming to here what is a homogeneous solution? C1, what is minus 1 whole power n plus C2n minus 1 whole power n. So because the two roots only there, that is why the roots are equals to minus 1. So here we have to find the C1 and C2 for obtaining the natural response. So here I am substituting for obtaining the natural response. I am considering n equals to 0 and n equals to 1. So n equals to 0, substitute. If you substitute n equals to 0 here, n equals to y h of 0 equals to C1 minus 1 whole power 0. Here n is 0 into something 0. So that's why only C1 is left. So similarly n equals to 1, if you get minus C1 minus C2 plus C2, then you will get y h n equals to 1. So from a homogeneous equation, similarly for obtaining this, I am substituting n equals to 0 here, also n equals to 1. Then from here y of 0 plus 2 y of m minus 1 y of m minus 2, because the equation is y of n plus 2 into y of n minus 1 plus y of n minus 2. So here I am substituting n equals to 0, means y of 0 plus 2 into y of 0 minus 1 is minus 1 plus y of 0 minus 2, that is minus 2. So already he is given the initial condition y of minus 1 equals to y of minus 2 equals to 1. So by substituting here y of 0 plus 2 into y of minus 1 plus y of minus 2, y of 0 is you don't know. So y of minus 1 is 1, 2 into 1 1 plus y of minus 2 is also 1, 1 into 1 1. So equals to 0. Y of 0 you obtain as minus 3. So that is nothing but C1 equals to minus 3. Then similarly we will get C2 equals to minus 2. So the natural response is by substituting this C1, C2 in this equation, we obtain the natural response. Like this, we have to find the natural response of a linear constant coefficient difference equation. So similarly, we have discussed another problem here. Y of n minus same. You have obtained that y of n equals to, and you have find the C1 constant, and here the initial conditions is y minus 1. Please make it as make down, and if possible, you can also do the problem. So this is our first unit, and we'll discuss in the next lecture the second unit. Thank you.